So thank you all for coming. Thanks BSides and the volunteers for doing all the work that they've done, and thanks PSU for the venue. You're doing a great job. I also want to thank the speakers that have gone before me. You've all done such amazing work that I really appreciate, but I want to say that after watching all the talks I've seen yesterday and today, I'm fairly confident I can say that this will be the second best talk about bicycles. Okay, so a quick word about me. I'm Will, an instrument-rated private pilot. I fly for Angel Flight West and Elevated Access. They are amazing organizations that you should research. After this talk, I'm currently the CTO of Savant Systems. They don't know about this talk. They have nothing to do with it. They just have no responsibility for anything I'm going to say. And we're talking about this bike right here. So my brother-in-law died a couple of years ago, and out of his estate, I got this bike from my father-in-law, and he said, "Hey, Will, we've got this bike. I think it's a Cannondale or something. Do you want it?" I said, "Yeah, sure, why not?" It took us a couple of years to deal with the logistics. It was in Arizona, blah, 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 and it showed up. And it's not a Cannondale. I don't know what it is. I've never seen it before. So I started doing the same kind of stuff that Bastardo Grande's talk did. I'm like, okay, well, what can I Google on this bike? What can I search for? So I searched for Flash, and I didn't find a lot, except that, oh no, I have no slide notes. Well, this is going to be fun. Except I found out that, well, let's see what I found out. I was able to power it on eventually. Like, it took me a long time. I didn't have a charger for it. It sat for like 3 years. And I kept plugging in the charger, and it wasn't really doing anything. But eventually, one day, I was brave enough to let it sit for a couple hours, and it booted up. I'm like, cool. What is that? And so I looked up the user manual, and I was like, oh, it's some kind of a passcode. So I was texting my father-in-law saying, hey, what are Scott's passcodes? What does he use for stuff? He sent me this Word doc of 100 passcodes. And none of them would fit into these numbers, right? And so he's like, oh, well, his birthday is, I don't remember what it is, but his birthday is, these numbers. I'm like, oh, sweet, they fit. So I was able to log into the bike, but I'm like, but now what? So I found out that you need the app for everything, right? It has this app, it pairs with Bluetooth, but I tried it and it kept being like, hey, you have no internet. I'm like, I'm pretty sure I have internet. Turns out that all of their servers were down. The cloud was down, the app was down, nothing was working at all. And so I was like, okay, well, this is a much bigger project than I had anticipated. But I was doing research about this Flash company, and I found out there's a VentureBeat article. And it's like, hey, this Zach Fountain guy, he started Flash. He brought on Kai Huang, who is the band, what's the name of it? The video game where you play in a band. Yes, yeah, he's Rock Band guy. And then, so they started this company, Flash, and this is their timeline, right? So in February 2016, they filed for incorporation. In 2017, they did an Indiegogo. They shipped in 2018, which actually, June to January, that's amazing for Indiegogo. 6 months, impressive. But they didn't sell anything after that. They did 666% of goal, which is sus, right? I would have thrown in the extra $10 to have that 667%, but that's just me. They didn't sell barely anything. They had a huge media blitz. They bought media from all the outlets, Verge, everything. If you could buy a paid editorial, whatever they were, they did it. But then by December 2021, their web store closes. By January 2022, it's just a Shopify landing page. And by May, they filed for a dissolution of the company. Now, this talk is a reverse engineering talk, but that's just the how. The why of this talk is freedom, right? The why of this talk is freedom from vendor lock-in, liberation from all of that crap. Reverse engineering is just a super fun way to get there. So just after I started, VanMoof went out of business. So there's tons of press about VanMoof going under, and I'm like, oh man, this is a bigger story than I thought it would be. This is a lot, right? And so all of these companies, these other e-bike companies are like, well, this is an opportunity and a risk, right? It's an opportunity because by far the biggest name in e-bikes dies, but it's a risk because all the customers are saying, well, what about you? Are you going to go under? Am I going to be in trouble if you go under as well? And if VanMoof goes under, there's tons of people that are impacted, and they're going to be hackers, people like us that figure out how to get around it. But if some mom and pop shop goes under, then if Flash goes under, that's not the case, right? So if we go back to this one, so another company, Cowboy Bikes, what they did when VanMoof filed for bankruptcy is they wrote a tool that lets you scrape the authorization key from their cloud that they use to then unlock the bike over Bluetooth. So they released a code that did that, and then they also made a mobile app. So you could still use your VanMoof bike with your Cowboy stuff. So that was pretty cool, right? So they're like making sure that people don't get stuck, and they're using that as a way to say, hey, we've got your back. But there's another company, Ampler, and their CMO had an interview about this time, and she was saying, we're different because we're not a hyper-growth company. So where VanMoof is all about taking VC, hyper-growth, and then IPO exit, right? Ampler was like, we're not going to do that. We're going to build a sustainable business that doesn't flash and go away, and you can rely on them. But the problem is, as I was looking at their product line, this is the head tube, not the head tube. This is like the main tube of their bike, and it's got this like beautiful inset integrated display. It's just like the Flash. You don't see any like e-bike parts. It's just really streamlined and beautiful. The problem with that is that all these parts are proprietary. So if for some reason market forces do force Ampler to go out of business, as the consumer, you're still in just as much trouble, right? Okay, so I want to just read this quote to you. When you make a product, what is your legacy? What value are you producing, and who's the beneficiary of that value? Clearly, it's important to build a sustainable business. Your customers are no better off if you go out of business. But if you're not producing durable value for the consumer, then I don't think you have a reason to exist. And in a functional market, you won't anyhow. I'm not saying we have a functional market. We don't. But if we did, right, then if you're not producing value for the consumer, then why are they giving you money at all? Okay, so let's get into reverse engineering, which I hope is going to be more sort of poignant for the group here. Again, this is the bike. We're looking sort of down from the rear tire to the front of the bike. And there's this sort of end cap here, right? In this photo, there are 7 security screws. Okay, 2 there, 4 on that charging port, and then 1 on you can't really see it, but the headlight tube has 1 there. Now, while they were doing that media blitz, they sort of coyingly said, oh, the battery is end user replaceable. Now, where's the battery? Anybody find it? Inside? Yeah, it's inside with security screws. And you have to take off the back tire. And I don't know if you've taken off the back tire on an e-bike, but it is not fun. It's super not fun, and it gets worse. So it sort of kind of pissed me off, right? Like, why are they letting reviewers say that, like, it's replaceable when it is not, okay? So I did some estimates. So in my opinion, a trained tech that has done this probably 5 or 10 times before would take at least an hour to change the battery. Okay. Oh, right. So what I wanted to say also is you take off this back cover, and in this back cover, there are a bunch of wires. So up going towards the top of the screen there is the ESC, which is the electronic speed controller. So there's like the battery connection, the motor connector, the throttle or the pedal sensor, the throttle cable, and the data cable from the main board is all back here, and a cellular antenna. Okay. So I got all that stuff out. I started to try to pull the battery out, but it wouldn't come out. So I unscrewed that charging port, and this is looking into that charging port. And this is the little LCD module. Okay, so we've got 2 10-pin JST connectors and 2 micro coax. But we've also got 2 button clusters, little brake, stuff like that up there. So you have to remove all that stuff too. And then it comes out. And now I've got it on the bench. And so what we've got here is we've got a 4S 10P pack. So that's 4 batteries in series, 10 in series, 4 in parallel, 10 in series. And then up here, this is the BMS, the battery management system. And then down here, that's the main board. So if you wanted to replace the battery, not only do you have to get it out of the bike, you also have to take it apart and then transplant the main board from one to the other. It's ridiculous. So this is sort of like a diagram of the architecture of the bike, right? So this is all the parts of the bike. The headlight, the little LCD module's got the GPS antenna and a Bluetooth antenna on there. The brakes and the buttons and the charge port and the mystery button, which I didn't really get into. I still don't know what the mystery button does. And then the throttle, and then we've got the ESC, the motor, and the pedal sensor there in the back. So, I mean, that's kind of cool, right? Like we're starting to make progress. We know how this bike is architected, at least. But our real goal is to replace the main board, right? Because the main board's got all that cloud stuff that we can't do. So we've got to figure out some kind of a plan for the main board. So if we redraw that diagram, but this time we're drawing it from the perspective of the main board and everything that's connected to it, right? We've got the LCD module again. Those are all the like connectors on the board that we need. And it's sort of like this big hub kind of a thing. It's kind of intimidating, right? Like, are we going to have to design our own circuit board to replace all this stuff? I hope not. But let's look at it and see what we actually need. So this is a closer-up photo of it. Down here, this is the ESC connector. It's a 8-pin JST, 2 millimeter. Here it goes to the brakes. And then we can see I've highlighted this wire here that goes through. So okay, the brakes are just like shorted over, they're just shunted to the ESC, cool, we can handle that. We got a little transistor, here's a MOSFET, and then that goes there as well. And then we've got 2 serial ports, 2 grounds. Like, okay, that's starting to feel tractable. Like maybe like this is all that we need really for the ESC, okay? But then what's all this other crap doing? Well, we've got a 36 volt power input, that's actually 36 to 42 volts, that's what comes in raw from the battery. These 2 big pins, those are the headlight and the tail light. We got the cellular module up there with its SIM card slot. And then we've got 3 channels of UART there over I2C. That's what those guys are. And then down here, we've got the main IC that is an Infineon Cortex M0. It seems like it's for the automotive market. The most interesting thing about that chip, in my opinion, is that it's got a peripheral architecture I haven't seen very much of. It is essentially like an FPGA, like the main chip isn't an FPGA, but like the peripherals are sort of like an FPGA, okay? And they give you like Verilog libraries for like common peripherals. So it's kind of clever, right? Like you're not like, I don't know if you've looked at shopping for microcontrollers, but you'll be like, oh, I need like 6 UARTs and 3 timers and whatever, and like you have this huge matrix of like chips you need. So this kind of like gets away from that. It's kind of a cool system. That's a digression though. And we've got the horn and then the LCD module connector down there in the bottom. But half the board area is power supplies. Okay, so like that's a lot of power supplies. So I reverse engineered that too. And so this is what the power sort of architecture looks like for the bike. We've got a battery coming in, 36 to 42 volts, and then we've got tons of buck converters. We've got a buck converter for the lights, the headlight and the tail light. They get their own buck converter that goes to 8 volts. We've got a main buck converter that goes down to 12. That powers the horn, but it also powers 3 others, 3.3 for the LCD module, 3.3 for the logic, 3.8 for the cellular. And you're like, why? Why? I have theories, okay? So, you know, when you're designing power systems, you're like trying to balance all these factors. There's BOM cost, like how much does this cost in just parts? Can I get these chips, like are they available? I don't know if any of you are involved in like manufacturing, but 2000, 2001, even into 2002, it's hard. Like TI has this huge, they almost have a lock on power ICs. And so, you know, can we get these chips? So like that's another factor you have to think about when you're designing power systems. But there's also efficiency. Like, are we burning a bunch of heat in this architecture? Are we like maximizing the efficiency of each of these components? But I think that most of their decisions here are really around like crosstalk and EMI. And what I mean by that is that these lamps, they flash, okay? And they're really bright, so they're consuming a ton of current. So if you don't have those on their own sort of supply, you run the risk of introducing transients on the rest of the power supplies when those lights blink. Okay, and same thing kind of with the LCD buck converter. Now, I don't think that actually is powering the LCD. My theory on that is that it's powering the low noise amplifier for the GPS. So if you were to have this LCD supply on the same as the logic buck supply, you could actually modulate the GPS signal going into the cellular module by signals of varying, you know, intensity from the microcontroller. So anyways, I think that they actually did a pretty good job designing this. But if you read the reviews of the bike, a lot of them will say that it had trouble with the battery pack getting dead if you let it sit in the garage for too long. And I think that this is partially to blame. They do talk about how they've got an accelerometer so you can detect if it's jostled, and it'll power the bike up, get a GPS fix, and then send it over cellular. And you know that's going to be on this logic buck converter, so that means you're running 2 buck converters 24/7 just to power that accelerometer so the bike knows it's jostled. And so, I mean, I think that partially, the engineers are to blame, but I think it's actually more likely, if you want to assign blame to somebody, it would be the product designers, right? The product designers said, oh, this is the architecture we want for the bike, or this is the feature set we want for the bike. And so they had to design it in a way to make that work, and the consequence is that it runs out of battery. Okay, now, this part of the talk is kind of a journey. So we're just going to go on this journey together. And what we're doing is we're looking at the battery management system. We're going to answer a couple of questions. Can we charge the pack? Remember, I only charged it up a little bit to realize that I'm kind of stuck without that app. I have a rad power wagon. Rad's in Seattle. They're a super rad company. And I have a charger for them. So can I make that charger work? And can the pack hold a charge overnight, over days, over weeks? And then can we communicate with it? Because at this point, I'm like, I might need to communicate with this battery pack. Because it's got a serial connector to the main board as well. So I devised some tests. So this is my bench again, and I've got the pack. I've basically put the bike back together without the frame on my bench. So we got the ESC there, we got the pack, the charger's down on the floor. I've got my oscilloscope set up super long time scale, so it's like a data logger basically. It's like an hour per division or something. And I'm measuring the voltage and the current. That's my little DC Hall effect current sensor there with the wire going through. And on the first day, I brought it up to 3.6 volts. I don't want to start a fire, right? So I want to ease into it. So I charged it up to 3.6 volts, let it sit overnight, and it only lost 1/10 of a volt per cell. So I'm like, yeah, sweet. So the next day I go to 4 volts, and still, it's pretty good. Yeah, sweet. And the next day I go all the way up to 4.2. So it turned out that, yeah, I can charge the pack. The rad wagon charger worked. The pack does hold a charge, but the communication format, I should have said that before because it's checked off. But the communication format, I hooked up my Salier to it, and it's 9600 baud UART. So I'm like, sweet, what could go wrong? And so I download all that data, right? Because I'm the whole time, my Salier is just sitting there log in packets. And so I've got my favorite reverse engineering tool. It's the best. You guys heard of it? It's called a spreadsheet. So you'd think it's Python, you'd think it's Wireshark. Nah, it's numbers. So I dumped all that data into numbers, and thankfully, all of the packets are the same size. So I just wrote a quick formula, and now I've got the data that's just streaming in, and it's in frames. So on the right there, I've just got the frames. And a couple of things stand out. Well, so right in the spreadsheet, you can select a column, and you can go summaries, and it'll say min, max, average, whatever. So columns 1, 9, and 10 were always the same. And 58, for those of you who know your ASCII tables by heart, that's a colon. And 13 is a line feed, and 10 is a carriage return. So we already know 1, 9, and 10. Now 9 and 10 on one direction, 8 and 9 on the other. Whether you're going to the BMS or back, they're different sides. But the point is we know the first and the last two. So we're doing pretty good. I just got to figure out the middle. While I was doing this, though, I remember I had it all hooked up to my oscilloscope, and I noticed these are the traces from the UART going to and from. This is to the BMS here. See, the tops are nice and crisp, and this is from. You see how they kind of have a weird arc to them a little bit? Let's zoom in. So if we zoom into it, this is what they look like. Now, if you spend enough time looking at I2C data, you'll recognize this immediately, because this is an open collector output, and what that means is that they have a pull-up resistor going up to some voltage, and then they have a transistor that shorts it, right? So that soft arc, when it goes up, that's the resistor charging the capacitance of all those wires, charging them up to a voltage, and then when the transistor clips, it just drops it right off. So I'm like, oh, cool. Okay. So that's my theory about how it was built. And then I spent some time looking at the board even closer. And these are opto-isolators, okay? So I'm like, yes. Because what happens is, what if you want to have the battery management system in your main board at different voltages? You're going to need to have some way to prevent those from messing each other up. So I'm like, okay, so this is the architecture now, and I'm pretty sure this is true. I don't want to actually go through and probe stuff because you can't turn off a battery. Batteries don't have power switches, and I chose life. So I just assumed that's what it was. But there's something weird about this architecture, right? If we have it set up this way, you can actually do this. And you can just chain them off each other, right? Because each one of those can just pull the line down. But is there any support for this in the packet format? And like, maybe. I only have one, but byte 2 is always 22. Always, always. So I'm like, well, maybe that's the address, like maybe an endpoint address, maybe that's the BMS address. Not sure, but I'm going to call it close enough, and we're just going to check it off, because why not? But byte 4 kind of looks like it might be a different kind of address. So we've got to the BMS, we've got from the BMS, and always if it's going to, it's 01, and always if it's coming back, it's 02. So I'm like, okay, cool. I think we've got to and from. Good enough for me. Let's just call that one good. Now we're looking at byte 3. So byte 3 is sort of standing there. It's like kind of sticking out like a sore thumb. And this is what happens if you just take all those bytes and just plot them. Again, numbers, right? Spreadsheets, it's all about spreadsheets. So I just took all 10 bytes of the packet and I just plotted them over time. Now it's super, super chaotic. So then you start like changing the sort order. And you can change the sort order to have like, column A first and then column B or whatever. So I sorted it by byte 3 and then by time. And when you sort it by byte 3 and then time, all of a sudden that chaos settles down. And we have some really interesting things pop out of the data. So down here, this teal blue line, every time that switches, that's a different value for byte 3. And if you look at the transitions, that sort of delineates blocks where the data looks like it's correlated or has a similar meaning, similar semantics. So I'm like, yeah, byte 3 is going to be some kind of a register address or something, right? So let's just call that one good enough. Okay, now let's go back. And there's one thing that pops out to me in this data, and that's, see this like sawtooth kind of thing, this green one that goes up and then down? And it's correlated right here with this gray one. Let's zoom in. So like that section right there. So this is what that looks like. So it goes up and then down, and then meanwhile that green one goes up just one tick. I'm like, yes, I caught a byte transition. And so that's what this looks like in the table. So it goes 255 to 0, and then this one goes up 1. So now I know that 16-bit integer. And I find out later it's assigned a 16-bit integer. So we can call those good. Okay, so we're actually, this is cool, right? Like, it's coming together. Like, we're getting there. Okay, now I'm gonna start talking about it from the back forward now. Okay, so like I think I've got the front part of the packet figured out. Now I want the back. So I'm gonna take that not applicable and I'm gonna move it over so we have them lined up vertically. This is sort of a nonlinear process, so I'm just gonna skip ahead and say, let's look at byte 7. And the reason I'm gonna say let's look at byte 7 is because if we go back to our graph, we can see that byte 7 and byte 5 have similarities. They have like some redundancy in that data, right? And so what does that mean? Well, redundancy is like literally what the R in CRC stands for, right? Like all checksums are redundant data by definition. So I'm like, there's gotta be some kind of a checksum. And I don't know if you guys, I'm skipping ahead. I don't know if you guys have spent time like trying to reverse engineer checksums, but it's like, kind of like you did a lot of guessing, right? Like, okay, what math is used to combine these numbers together? Which bytes are included? Luckily, this one's really simple, and it's like literally just a simple addition. So you just take bytes 2 through 6, add them together, mod 256, and like you're done. So now we're done with byte 7. Okay, so if I can guess what my next slide is, yes. So byte 6 and 8 going to the BMS from the main board are always the same. One's always 0, one's always 1. And so that's good enough for me to say, yeah, I can write my own packets to the BMS now. So like I have everything I need to write whatever I need, whatever commands I need. And I've only got 1 byte left to figure out coming from the BMS. Now I captured a bunch of data and I did my best to infer what this means. It's almost always 0, except for like 15% of the time it's 1. So this was my theory. This is the best I came up with. So this check 2 byte, that's what I'm calling it. If byte 6 is less than byte 4, it's 1. Otherwise, it's 0. But it doesn't work. So I wrote a program to like talk to the BMS like over hours, but like it doesn't work out in all cases. So I had to just like abandon it. But it doesn't matter because it's from the BMS, so I can just like not validate it. And so that's what I ended up doing. So that's fine. So I just marked that one caution and kind of move on. So now what I can do is I wrote a logger in Rust. So just a really simple program. It just knows how to talk to the BMS, get some registers from it, print them out in a CSV, and then I let it sit for hours while I was charging the battery. Remember, this is all happening like while I'm doing those initial tests where I'm just like charging it up. And so these are graphs that I took out from registers. Now, because even though I know the packet format, I don't know what the registers mean yet. I just know that like the number 5 gives me this graph, and the number 7 gives me that graph, right? So these are the most interesting ones. Now, the top left, and remember, I already know they're 16-bit integers, so I'm like, okay, well, what could these possibly mean? So we're starting at like a little over 32,000. I know you probably can't read that. And then it's shooting up to like 34,250. And remember, I've got like my scope running, so I know like what the pack voltage is, and it like, luckily, it's gotta be volts, right? Because it matches, it's close enough. We've got millivolts technically, but we've got volts. Okay, meanwhile, we've also got amps because we see it going from 0 to 2,000, and I know that at the end of charge, it was doing 2 amps, so that's 2,000 milliamps. And then this one, I think, is state of charge. I don't know for sure. It's my best guess. These ones, they're just playing me for a fool at this point. I have no idea what's going on. So this is just the help from that logger I told you about, the Rust program. Super simple, port, baud. It just does its thing. Now, don't hit me up too much about the like formatting of this. I was like an hour that I just threw it together, so it's a little jank. I'm gonna say that right up front. Now there's one last thing I want to talk about, and this is right at the end of charge, which is a super interesting point in the battery's like life cycle, right? Like when you reach full charge, you'd expect a lot of interesting things to happen, and indeed they do. So we see the unknown one is, oh yeah, I haven't talked about unknown one yet. That was this one. This one's unknown 1. Okay, I still have no idea what it is, but it could be temperature. So I have it as 2.98 here, but if you move the decimal point over, it could be 29, which is like 85 degrees Fahrenheit if you assume that's Celsius. So I'm like, yeah, that's probably Celsius, but I'm not sure. We know voltage, we know current, those make sense. And then that SOC one I talked about, you can see that once it gets full charge, it like shoots up from 93 to 100. So I'm like, that's probably state of charge. We got that one down. This next one, I have no idea. It's like always 2 or 3 below the other SOC, but like why? I don't understand that one at all. If you have any ideas, hit me up. Okay, and then the last one, this unknown 2, 128 is a really suspicious number, right? When you see 128, you're like, what's up with you? And so yeah, so it's like, it's usually 128, except when we hit full charge, we get this bit and we get these 2 bits. And so my best guess is this is some kind of a bit field. I don't know what the bits mean, but I'll put money down that it's some kind of a bit field. And then when it comes off, when it naturally comes off full charge, we lose 2 of the bits. We lose the highest bit, and I think we lose bit 5, something like that. So I'd be fascinated to know what those are. There's a couple of registers that always do the same values. One is always 3375. I'm pretty sure that's going to be some kind of like a low voltage, like minimum voltage thing that the BMS would kill the battery on. 4200 is going to be a max voltage for a lithium ion, and then 3600 is like nominal voltage. So those kind of make sense, but there's a ton of registers. Like that program I wrote, I just like, give me all the registers. Like up to 50, just like ask for all the registers. Even way more than like the main board ever asked for. And like at some point it just stopped responding. So I'm like, okay, it'll probably only implement up to like 25 or something. Or 30, I don't remember. Yeah. So this is the back. This is like the back of the battery. So if have you seen this battery? If you know anything about it, if you've heard of it before, if you know the company, if you know anybody there, I would love to hear from you. This model number, that model number, they don't appear in search at all, as far as I can tell. So it's kind of a mystery. I've even looked at Smart BMS, Yoku Smart BMS. Yeah, my search food just did not work out for me. Okay, so really an e-bike is like 4 components: battery, an ESC, a motor, and like some way to control it. So we've got the battery, the ESC is next. Now, it's really important to me that I not have to replace the ESC. And there's a reason for that, because the motors are in like ESC, their pairing is really important. And there's tons of like tuning parameters and like finicky things you have to get just right. And they've already tuned it. I don't want to have to redo it. So I'm going to do my best trying to figure out what we can do about this. Again, I don't know anything about it. They never talked about it in any of the specification sheets. But it's got this prominent ASI debossed in it. So I'm like, cool, let's just search ASI. And like it turned out that like that was super easy. Like it just pops up. It's like, oh, accelerated systems, cool. So I was able to go on their site. I was able to find, this is probably a back 550. They have, like, they're meant for OEMs, so they have like specification sheets online that like have pinouts and everything. And so like I got the pinout and like this is the harness that it's wired up to. I toned out all of those connectors. They all made sense. They all went to sensible places. I'm like, sweet, I know what this thing is. And I figured, well, what if I just like plug it into the bike, right? And like see if I can, and the main board isn't in here, right? So this is just the ESC, the motor, and the battery, okay? So I'm like, can I just like use it? Like, what if I just short the battery loop? And what if I just like short the little enable pin on there that transistor way earlier did? And like, no dice. The pedal didn't work, the battery or the throttle didn't work. And then I went back to the manual, and the manual says, when you turn on the bike, it will start on pedal assist mode 0. And it's like, oh, if you want to use the throttle, it has to be in pedal assist mode 1 through 4. So I'm like, well, so much for that. So I'm like, okay, well, I better start researching the ASI display protocol. And as I was searching for that, and actually another company, I don't know if their SEO is just super good or what, but like this egg writer company popped up as the first hit under ASI display protocol. And they have a knowledge base that says, oh, here's how you set up your ASI speed controller with the egg writer. I'm like, yeah, I don't have to make a display? Yes, thank you. But it's like, set these parameters. And I'm like, what? I don't know how to do that. I don't know what you're talking about. And so I emailed, who did I email first? I think I emailed both of them. It was super annoying. I was like, every sales engineer, like, contact us, email address. I just started emailing Egg Writer and ASI. I'm like, please help. And let's see. Okay, yeah, so I emailed ASI, and then they sent this message back. The controller is programmed for that specific setup, and we do not give out software to end users. Even if you were to gain access through other means, I'm reasonably sure the parameters are locked and unreadable. I'm like, okay, challenge accepted. So they will sell you this kit, okay? This is the eval kit. Now, the cool thing about this kit is that it's got, all the stuff you need. Like, this is like a galvanic isolator for ESC, so like the voltages are fine, and like it's got the little like TTL USB adapter thingy, and it comes with a copy of their backdoor software. But it's $750. I'm not going to pay that. I paid $0 for the bike. This is infinite times more cost than the bike. So I was talking to my friend. I'm getting ahead. I was talking to my friend Andrew. From work, and he's like, let me see what it was. Oh yeah, so I need to hook it up to the computer, right? So it's got this connector on the end. And the nice thing about this connector is like all 4 pins you need to connect to the computer are like right next to each other. And I've got all these 2mm JST connectors I don't need anymore. So like, what if I just do that? I'm like, yeah, it works. It works just fine. But like now I need software, right? So now I'm going to my friend Andrew, who told me like, well, there's this company, Grin Technologies, and they make something called Phase Runner. And Phase Runner uses the same Modbus map as ASI does. So why don't you just use their Phase Runner software, because they'll give it to anybody. And you can probably do everything you need to do. And that like kind of worked. I could like get a snapshot of all the Modbus registers, and I could like look at them a little bit, then it kind of like froze up and crashed, and like it wouldn't save over reboots. So I was like, oh, god damn it. But can you find a copy of Backdoor online? And like, yeah, you can. So on the forums, Andrew's like, oh yeah, I found it. And so I was like, okay, cool. So now I have Backdoor. But what can I do with Backdoor? I can like hook it up to my Salier, and I can get all the communication. Like I can see what Backdoor sends to the ESC. I can just copy that. And so this is all it does. It just writes a register using Modbus. It verifies that the write went correctly. And then to write to flash, you just write FFFF to 0x1FF. And like, that's it. That's all Backdoor does. And so I'm like, really? Like, why are you restricting access to this software tool that just implements standard Modbus? Like, it's nuts to me. And like, you can, if you're curious, you can go online, and on GitHub, there's like an XML document with all the ASI Modbus registers, what they all mean, what their values are, what the enums map to. It's like, it's all open. Like, I don't understand. But one way or another, we've got a program. I've got a link to it in the talk. If you end up with this bike or with this speed controller, you can use this program and knock yourself out. So can we just implement Modbus? Hell yes, we can. But what about those locked parameters that he talked about? And like, I was searching for that, and I spent a ton of time in their knowledge base, and I found tons of articles. And this one's really interesting. So what you can do with that backdoor program is download an XML of all the registers of your ESC so that you can like update the firmware on it and then reload those registers back. Or you can like take a snapshot and you can like tune the bike and you like go back to like a given snapshot. So this knowledge base article says if you took a snapshot and then you updated your firmware and then you loaded a snapshot back from the old firmware, you will brick your speed controller, okay? And here's how you unbrick it. Okay, now that's cool and that's exciting. Basically what they say is you could look in that XML document, you look for 130, because they took a register that was used for something else, they made it a locking register, and then people were accidentally overwriting that locking register with some random value. So like look for the value you had in yours, and then put it in there. But it will only work for controllers that were locked inadvertently due to parameter install. Parameters that are locked by OEMs have their own unique password set by the OEM, and cannot be locked in this manner. Nice try. And like, really? That's your tone. It's the wrong tone. Like, you're talking to my guy all wrong. So I kept reading, and I found that like there's this tamper-proof functionality as required by ISO 13849. I'm like, it's starting to make more sense. Now it's clear to me that there's this ISO standard, and they require e-bike vendors to make sure that end users can't like change the speed limit or like change the power of your bike, because there's like they're classified. There's like class 1 bikes, class 2 bikes, class 3 bikes. I'm like, okay, this is starting to make sense. And here's that address 62 again that I showed earlier. But this part stood out to me. Can anybody raise your hand and tell me why that part might have stood out to me?
That's a 16-bit integer.
Yeah. Exactly. That's not a lot of numbers, right? Like, we can just crack that. Like, yeah. And so it takes like an hour. Okay, so like you just set up a Modbus thing and just like iterate through these numbers. It literally takes less than an hour to like explore the key space and unlock all the parameters. There's another parameter that they have though. This one's user access level 1, and I love the name of that. It seems so like, I don't know, it's like Half-Life or something, I don't know. And so this one's different though. This one is actually really important for safety. So much so, I don't fully understand it. I'm not like an e-bike engineer. But the reason why this one's important for safety is that it essentially changes the way that the ESC energizes the coils. And so you can get higher rotational speed than would be implied by the voltage of the pack. Okay, so like motors have this KV number, and I think it's all kind of related. But they're like, hey, you can change this parameter that will let you sort of overdrive your electric motor. But they don't say it in here, but they say later, like, there's a reason why we lock this. Like, it's important that you use this for safety. And so this parameter, though, like, remember said the other one, the access code is set by the OEM. This one's set by ASI. And if you are an OEM and you want to change it, you talk to your sales engineer at ASI, and then they will give you the code. You can crack it, too. Just as easy. So, I mean, it's like, it's completely ridiculous. So this is the program I said that's online. If you find yourself with a bike that you want to deal with, you just set the baud, the port number, and then if you want to like do all the setup for Egg Rider, you just pass it Egg Rider, and it'll just do it. But it will give you an error if it's locked. It'll be able to detect if the bike is locked. It'll say, hey, you need to give an access code, and you would pass it here with access. And you can say whatever number that is. It's the register 62 thing. But if you don't have it, then you've got two options. You've got crack, which will give you the value of 62, and you've got crack OEM, which will give you access level 1. And like I said, it takes less than an hour for each. Yeah, so for the love of God, please do not do anything stupid with this information. Like the field weakening, they're pretty serious that like you can hurt yourself with that. So just don't. Yeah, so like really just use this if your bike was abandoned by the manufacturer and you want to be able to keep using it. Okay, now there's another thing that came up in this, and like I kind of got spooked a little bit. I have friends that are in the e-bike industry that have worked with ASI, and so I sort of floated him the idea. I was like, are they going to be mad at me for this? And he's like, yeah, they're going to be pissed. So I contacted the EFF, and I like went through the whole system to like make sure that I don't have to do responsible disclosure and everything else. And I found in that due diligence, I found a post from 2021 where somebody else discovered how easy it was to crack that password, and so That's good news. EFF said I'm clear, so I do want to say great thanks to EFF for all the work that they do. And let's move on. So the Egg Writer, their business model is essentially third-party displays for bikes that exist, and that's really what it's designed for. So when you try to buy one of these, they go through this flow. Like you can get your ASI, what bike is it, what connector does it have, and they'll either support you or not. And I emailed them, I said, hey, I've got this other bike, will you support me? They said no. No warranty, no support, nothing, but they didn't stop me from buying it. So I just said ASI, and I got these are Gillette connectors, so I got like a round Gillette connector. They published the pinouts online, which is awfully convenient of them. And then I wired it up, and I sort of did this kind of a same bench test, right? So like I put it on my 0.1-inch headers, used breadboard jumpers to like wire up the Egg Writer to the rest of the bike, and it worked perfect first try. And the app came up, and it was like over Bluetooth and everything. And you can set all these parameters, like the current and speed, and they sort of trust you to like know your local laws and everything else. They let you change the field weakening percent. That is that access level 1 thing. So they actually let you edit those settings through the app on the bike. So in principle, you could like edit that while you're riding, which seems insane to me. Yeah, so like, okay, how do we actually like wrap this thing up? How do we close the loop of I've got this bike, I've got a bunch of crap on my bench. And so if we sort of like look back at the bike architecture and like really just focus in on the things that we need, this is that old main board with the 8-pin JST and the bike, and those are the factory cables. Like we can just cut those cables. And if we just cut the cables, then we can have just a commercial extension cable, like those Gillette cables. You can get them on Amazon. They're like $3. So I got the 5-pin Gillette that the Egg Writer needs. That's the existing cable for the brake, and I just sort of lashed it together, soldered them together, made the thing, used some glue line, heat shrink, squished it out flat because it's got to fit in the bike tube next to the battery there. And it works. It's amazing. So I've put like 100 miles on the bike. It's like, so I've got a rad wagon. So the rad wagon, if you don't know, it's like a huge bike, and it weighs like 80 pounds. And I'm used to riding it around with my 10-year-old on the back, so like I'm used to like 300 pounds of bike and people. And so this bike weighs so much less than that, and even though it has about the same amount of power, it feels like I'm on like a Ferrari or something. So it's been pretty fun. Although I can tell that like it's not as well tuned as the rad wagon. The rad wagon is like so smooth, but this one you got 20 kilohertz switching whine, and like the motor has a lot of commutation noise. So like, it's not as refined, but it works really well. Now, there's another thing that the Egg Writer does, and that it does logging. So when you have your app open while you're riding around, it will give you all these cool logs. This is like a 10-mile ride I did. This is kind of interesting and cool, too. So this here, you can see there's tons more current out of the ESC than later on. And it has something called like fold back. And so like if your battery is low, it will fold back the amount of current you can use. If the ESC is warm, it will fold back the amount of current. So what I think is happening here is I'm like riding hard, and then the ESC gets hot, and then it folds back the current, and you can see it all in the graphs. It's pretty sweet. So want to give some closing thoughts. I'm still writing about this, so this is a screenshot of my blog. This is the newest post on it. There's no way I could have fit the head and tail lamps reverse engineering into this talk. It's probably another 10 or 15 minutes, but it's online now. I have an idea, like this is one of those things like I need a new project, like I need a hole in the head, but I can't help myself because I want to replace the main board with like something cool, maybe ESP32, C3, running Rust, and like using the existing LCD, and make the horns work, make the lights work, just fun stuff like that. There's another idea I have to do an interposer between the LCD and an existing, like a factory main board that could crack the pin code using like skimming the SPI data from the display, like injecting I2C button presses. I haven't thought that one through very far, but it'd be kind of a fun thing to do. And so there's a couple of like philosophical things I want to say. And I go to a lot of WDCs, at least I used to go to a lot of the Apple conferences. I went to like 8. And one of them, Michael Fronte, was the Apple Bash music act. And I don't know, but I really like Michael Fronte. And he said something to the crowd that really stuck with me. And he said, all of you here have a gift, right? All of you here are because you either have the ability to do this work, or you have a company that's willing to pay for you to like go to this talk and like learn these techniques and these tools and express yourself in code and in technology. And I hope that you use that for good, and I hope that you use that to make the world a better place. And so as you're doing your technical work, what choices are you making? What's the impact of those choices? What choices are manufacturers making? Can you as a consumer make choices that help put pressure on manufacturers that aren't making as good of choices, that aren't supporting sustainable, like maintainable long-term value out of their goods? I want to thank everybody. I want to thank my family for dealing with the torn apart bike in the garage for 4 months. The Electronic Frontier Foundation for giving me the wonderful advice. Derelict Robot, that's my friend Andrew's company. He's gave me a lot of help on this project. And finally, BSides PDX. And these are my socials. Thank you all for coming.